All right, what we're going to be talking about now is looking at which direction a reaction is going to go when it's not at equilibrium. Okay, so one way we can look at this sketch is if we had something like a reaction of A going to B, all right, and it had some value of Kc. What happens, the way I like to look at this drawing, is that a reaction can look something like this. And we'll define these axes much later when we get into thermodynamics. But at any rate, kind of the way I want you to think about this is if it were a bowl, all right, and we would drop a ball bearing in that bowl somewhere, and it would just kind of roll around, and then it would stop at the very bottom eventually, all right? And that's that point where we call equilibrium, okay? So if that ball bearing was dropped here, which way is it going to go? All right, well, it's going to swing in that direction to reach equilibrium. All right, now it may actually pass it, right? It may go kind of like a skateboarder past that point there, and then it would come back down. But nonetheless, if our ball bearing was at this point here, it would trend down towards the Kc. All right, now we put the ball bearing over here. Of course, it's going to trend down in that direction. All right. So what I like to do when I'm looking at these is I would say this is the A and the B enrichments. And what I mean by that is when you're on one side of Kc, which this is larger values than Kc, and these are smaller values than Kc, we can kind of tell that if we have an equilibrium mixture that's over here, it's going to tend towards B. It's going to make more B and consume more A. All right? If we have an equilibrium mixture and we're sitting over here, it's going to tend towards A and consume B. All right? And the way we can quantify that consumption of one or the other is something called the reaction coordinate. All right? Or sorry, reaction quotient. So it's called QC. And this is known as the reaction quotient. All right? And QC is defined in our particular reaction as the concentration of B at some particular time and the concentration of A at some particular time. All right? And Q can have three different results. QC could be equal to Kc. When that occurs, reaction is at equilibrium. All right? So on our little plot, that means we put the ball bearing right at Kc. All right? We did a perfect drop, and it's at equilibrium. So if it's at a perfect drop and it's at equilibrium, which way is it going to move? Is it going to move towards A or is it going to move towards B? And the answer is it's not going to move either direction. All right? It is right there at the equilibrium. Okay? What happens when QC is, let's say, larger than Kc? All right? So again, QC is equal to the concentration of B time T, where Kc is equal to the concentration of B at the equilibrium and A at the equilibrium. So if QC is too big, what does that mean? We've got too much what? We've got too much B. All right? So where would we be in our little bowl? All right? If we've got too much B, that means we're up here somewhere. All right? And which way is the equilibrium going to, or sorry, which way is the reaction going to start going in order to get down to Kc? In order to reach Kc, B is going to have to start getting consumed, and A is going to have to start getting produced. So the reaction is going to trend to the left, all right? That's if our QC is too big. The next scenario we can have is QC happens to be smaller than KC. So if QC is too small, QC is too small, that means we got too much A, and we dropped our bearing over here somewhere where it's too much A, and it's going to roll down to KC. So if QC happens to be too small, we're going to start consuming A, and we're going to start producing B. All right? So just keep that visual in mind, and if you can kind of pretend that, you know, Q or KC is at the bottom of this bowl, all right, and then you have your reactant side on the left and your product side on the right, and where you drop that ball bearing is going to tell you which way the reaction will shift to arrive at the bottom of the bowl, KC. All right? So again, QC equaling KC, you dropped it right on the right point. Okay? QC is too big, too much product. So we're going to course correct by consuming the product and making the reactant. And if QC is too small, that means we have too much reactant. So we'll course correct and move towards the product side, consuming the reactant. So we can look at this mathematically by considering the following reaction. If we take iodine gas plus chlorine gas, and this makes 2 moles of a molecule called iodine monochloride. And it has a Kp equal to 81.9. Right, so Kp again is just the equilibrium constant for partial pressures of gases. All right, so let's say this mixture contains partial pressure of I2 equal to 0.114 atmosphere. Partial pressure of chlorine is equal to 0.102 atmosphere. And PiCl equal to 0.355 atmosphere. Are we at equilibrium? If no, which way are we shifting? Or which way are we headed? All right. So, easy way to do this is you just calculate Q, and then you compare Q to K. So, calculate QP. So, QP, products over reactants. So, it's ICL, partial pressure of ICL squared over the partial pressure of iodine times the partial pressure of chlorine. So we plug those in, 0.355 squared over 0.114. And again, Q, much like K, is unitless, so we can kind of drop the units as long as we're all dealing with atmospheres here. All right. If they were all in millimeters of mercury, that would be totally fine too. All right. As long as they're all the same units, that's all we care about. So I'm going to go ahead and multiply these out. And I get a value of 10.8. And that's my QP. So if QP is 10.8 and KP was 81.9, what can I say here? QP is too small. All right. So where did we drop our bearing? So this is the too small side. This is the too large side. So think about it. Too small because we haven't got there yet. Too large, we passed it. All right. So QP is too small. So we're going to do what? We're going to move to the right. Thus, we are going to make more ICL. Okay. So too small of QC, or in this case QP. All right. QP is smaller than KP. We have too much reactant. Reaction will continue towards products. All right, next thing we're going to move into is finding equilibrium concentrations. All right, so this is going to require some math, and we're going to split it into two different things. The first we're going to look at is much simpler. This is going to be looking at the equilibrium constant. We know that value, and then we have the value of all the reagents except for one, and we just got to find that one. All right, and the reason that may be important is because if you have a reaction and you know its equilibrium constant, you may want to know how much of the product you're going to wind up producing here. All right, so it helps you predict amounts that will be necessary in reactions. The second part we're going to be looking at is we're going to be trying to find equilibrium concentrations when we know the equilibrium constant and only the initial concentrations of the reactants. All right, that's, or in some cases products. That is very, very powerful, yet it's more complicated. So let's just start with the first. All right, so what we're going to be looking at is finding the equilibrium concentration when we know K and all but one of the equilibrium concentrations. Of reagents. When I say reagents, it's a generic term for both reactants and products. All right, so let's take a look at an example here. We're going to look at the following reaction. We take COF2, 2 moles of it, and it will decompose. Pardon me, that was in the gas phase. To give us CO2 gas and carbon tetrafluoride gas. And we have a Kc is equal to 2.0 at 1000 C. All right. And they measure an equilibrium measure, or equilibrium mixture. We have the concentration of COF2 is 0.255 molar. And the carbon tetrafluoride concentration is 118 molar. What is the concentration of the CO2 at equilibrium? All right, so a few things I want to point out. This is at equilibrium. All right, so we don't have to worry about the reaction quotient or which direction the reaction is headed. All right, we know that ball bearing is sitting at the bottom of the bowl, and everybody's in a dynamic equilibrium, so we're relatively static. So the only thing we need to do is kind of just set up our equation and see what we're missing. All right, so if we're talking about equilibrium and everything's in molar, so we're going to say Kc. Well, Kc is going to be the reactants over the products. And in this case, that's CO2, carbon tetrafluoride, and COF2. All right. And what are we given at this point? Well, we're given the CF4 concentration at equilibrium. We're given the COF2 concentration at equilibrium. And in fact, we're given Kc at this temperature. So the only thing we're left to solve for is just a little bit of algebraic rearrangement to give us CO2. So that's not too bad. Oops. One major mistake I'm making. There's a 2 there. All right, coefficient of 2. So I need to adjust my equation to put a square there. All right, so it's still going to be just some algebra, but don't forget that square. All right. So if I'm going to rearrange for CO2, so I'm just going to go ahead and rewrite the equation here for us. I'm going to multiply both sides by the denominator. And divide by CF4. That'll give me CO2. All right. So I'm going to go ahead and plug in those values. Let's see, the COF2 was 0.255 squared, and my value of Kc was 2.0. And my value of CF4 was 0.118. That'll give me CO2. So I'm just doing some punching in the calculator here. I got a value of 1.10. And what are my units here? Well, concentration of CO2, molar concentration. So it's molar. All right. So that's rather straightforward, not too terribly difficult, just a little bit of algebra there, and don't forget your exponents like I almost did. Now we're going to move on to the second type of example, which is a lot more difficult, but actually much more useful. All right, so what we're going to be looking now is finding the concentrations at equilibrium when we know the equilibrium constant value and the initial concentrations. All right, so this little I here, that is going to be our molar concentration initial, and that is our molar concentration at equilibrium. All right, so what we're actually doing is we're starting the reaction off away from equilibrium, and we're going to try to be finding out what the concentrations will be when it actually hits equilibrium. All right, so this is very useful. All right, you put two reactants together and you let them rip, and you want to figure out what their concentrations of everybody in that vessel is going to be at the end of the day. All right, so and that's going to require something called an ice table. All right, so let's go ahead and look at an example and go ahead and use our ice table. All right, it's easier to just work through something, and we'll see it first hand before we try to define what the heck an ice table is. All right, so let's look at our chemical reaction where we take carbon monoxide gas plus 3 moles of H2 gas gives water and methane. All right. So what we're going to say here is a 1 liter vessel is charged with 1 mole of CO gas and 3 moles of H2 gas at 1200 K. Reaction is allowed to reach equilibrium where 0.387 mole H2O are found. What are the equilibrium concentrations of all other reagents? All right, so this is a big problem. All right, so let's kind of read through what's going on. So we have a 1 liter vessel, and they give us not molar concentrations, but actual moles of these guys. All right, that's something we haven't seen yet. But what's nice is molarity, or concentration, is mole per liter. And fortunately, we are faced with a 1 liter vessel. So in this case, you can just go ahead and say moles equals molarity, right? Because of the nice part of having a 1 liter vessel. So that's nice. What else are we dealing with here? 1200 K. All right, well, that's nice. They're just telling us it's operating at that temperature. Okay, reaction is allowed to reach equilibrium where 0.387 moles of water are found. What are the equilibrium concentrations of all the other reagents? All right, so this thing is just screaming for an ice table. All right, and let's go ahead and set up what an ice table looks like. So when the first step in making one of these tables is I like to write the chemical reaction, and it must be balanced across the top. Then I will go ahead and make this kind of axis system here. And in this little corner up here, I'm going to write molar, right? So, or an M with brackets around it, or sometimes just the brackets. What that is telling me to do is that everything in this darn table better be in molar, all right? I don't want any other funny units. It's got to be molar, all right? And then, hence the name ice table, I write the 3 letters I, C, and E. And they essentially mean I for initial, C for change, and E for equilibrium, all right? So what that means is I'm going to write the molar concentrations initially across this top row underneath each column, or sorry, under each reagent is corresponding to that concentration. So reading back through, I look at the carbon monoxide. I had 1 mole in a 1 liter vessel. So that means its concentration initially is 1 molar. All right. Hydrogen. We had 3 moles in a 1 liter vessel. So its initial molar concentration was also 3. Right. Recall, these are going to be all molar concentrations. So you don't have to write M after each one of them because we're saying right here We're dealing with molar. All right. So before that vessel was charged, it didn't have any water and it didn't have any methane in it. So the values for water and methane are going to be 0 at initial. Okay, so now we have to figure out how are they going to change. All right? Well, if it's going to get to equilibrium and you just put the reactants in there, they're going to have to be consumed and then the products are going to have to be produced. All right? So that means they're going to have to change. And that's where the C comes in. All right? So how do they change? Well, if this is a reactant, it's going to get consumed, so I'm going to put a minus sign. And it's going to get consumed by a factor of X, whereas this guy gets consumed by a factor of 3X. Now, what is X? That essentially is the factor what they're going to get changed based on stoichiometry. All right? So the CO is going to get consumed one time, right, because it has one times X because it has a coefficient of 1 in front of it. The hydrogen, however, is going to get changed by a factor of 3X because it has a coefficient of 3 in front of it. Now, moving over to the products, they get produced, so we're going to get a plus for these guys. Coefficient of 1, so it's just X. All right? Finally, the methane is going to be plus X. All right. So then we have, finally, the equilibrium concentration. All right, so what is the concentration at equilibrium? So all you do to get that is add I plus C. So it'll be 1 minus X, 3 minus 3X, 0 plus X gives me X, and 0 plus X gives me X. So right here, these are the concentrations at equilibrium for each species. 1 minus X is equal to the concentration of the carbon monoxide at equilibrium. X is the concentration of water at equilibrium. All right? Which is kind of cool because this one was very nice and they told us something. Reaction is allowed to reach equilibrium where 0.387 moles of water are found. All right? And it's still in a 1 liter vessel. So we know the concentration at equilibrium for water. All right? How? Well, they told us how many moles are in there in a 1 liter vessel. So X is actually equal to 0.387 molar. So we know what X is. Man, that made this a lot easier because now we can go through and say, all right, my concentration of CO at equilibrium was equal to 1 minus X, which happens to be 1 minus 0.387, which is equal to 0.613 molar. All right? Concentration of H2 at equilibrium was 3 minus 3X, which is equal to, punching in a few numbers, I get 1.84 molar. All right? And of course, water, it's the easiest one because they gave it to us, is equal to X at equilibrium. Excuse me. And it's 0.387 molar, as was methane. Okay, that was pretty easy as far as ice tables go because of that one key factor that they gave us X at the end. All right, very cool. Point of this problem was more to show you about how to use an ice table. All right, and they get a little more complicated. So what we're going to do next is look at a little step up on the difficulty meter. All right, now we're going to look at a little more rigorous of an example and take a step-by-step process. As I mentioned, these are going to be the most complicated of the examples that we're going to work. But if you can follow this systematic approach, all right, and take your time with these problems, you should have a lot of success. All right, so make sure you follow these steps. All right, so let's go ahead and look at a specific example where we're going to be looking for the equilibrium concentrations of a reaction if we're given the initial concentrations in the equilibrium constant. So this is exactly what we did in the previous one. All right, we needed an ice table, but we're going to leave out a little piece of information that makes it a little more difficult. All right, so let's see. Let's just go ahead and get started here. Let's take a look at a reaction. We're going to take N2 gas and oxygen gas, and I'm going to make 2 moles of NO2. NO gas. And this reaction has a Kc at this particular temperature of 0.10, and that's at 2000 degrees C. All right. So that's the information that we're provided. And then they're going to give us a little bit of a paragraph here, and it says a reaction mixture at 2000 C initially contains a concentration of N2. Okay, so N2 initial at 0.2 molar, and a concentration of oxygen initially at 0.2 molar. Find the equilibrium concentrations of all reagents at this temperature. Okie doke. So what are we given here? That's kind of what we need to read through. We're given the equilibrium constant. That's going to be critical. All right. We're also given initial concentrations of 2 reactants here. All right. We're not given any initial concentration of the product. We can assume that it is 0. All right. At this point, we're just given the N2 and the O2. We charge that vessel with those 2 gases, and we let it rip, and we're going to see where everybody falls out at the end. All right. So this is going to require the ice table, all right? But before you construct the ice table, we have to take what seems like a trivial step and calculate QC very quickly, all right? The reason we have to calculate QC is because there are going to be cases where you're given a little bit of the product as well, and you need to know which way the reaction is going to go. This honestly is a trivial case because if you just put the 2 reactants together and you have no product, well, you know you don't have enough product yet, so the reaction is just going to go. But let's just do this to be rigorous. All right, so QC in this case, all right, happens to be the concentration of NO squared over the concentration of N2 times the concentration of O2. And I said this is trivial because the initial concentration of NO2 is 0. And these guys were, it doesn't even matter, but we're just being complete. They were 0.2 times 0.2, and of course it's equal to 0. So QC being equal to 0 and KC being equal to 0.1, we know that QC is too small. So making product and consuming reactant. So this reaction is going to move to the right or towards products. Okay, so again, this is trivial because we knew that was going to happen because we don't have any NO to start with. All right, so that's step 1. Look at your QC. Step 2, build your ice table. All right. So the way I like to do it is you write your reactants plus products to give Just write your darn equilibrium expression. I don't know what I was trying to say there. So NO. Okay. This guy is going to be in molar. Okay, we got I, C, and E. All right, so initial, we knew the initial concentration of the nitrogen was 0.2. Initial concentration of the oxygen was 2. And the initial concentration of the nitrogen, or the NO, nitrogen monoxide, 0. All right, and how are they going to change? All right, so Q told us that these guys are getting consumed. So minus X, minus X. All right, they have a coefficient of 1, so that's it. This guy has a coefficient of 2. And he's being produced, so it's plus 2X. All right. Then we're going to go ahead and write the equilibrium concentrations. 0.200 minus X, 0.200 minus X, and 2X. Now, we weren't lucky. They didn't give us the equilibrium concentration of anybody, so we can't directly solve for X that way. All right. So what we're going to have to do now is set our equilibrium concentrations to K. All right? How can we do that? Well, we know that Kc is equal to the equilibrium concentration of the NO at equilibrium divided by the N2 at equilibrium and the O2 at equilibrium. All right? And we know those numbers from our ICE table. All right? We're going to take those out of the ICE table and put them into our expression. So NO from our ICE table was 2X. And that needs to be squared. We know N2 from our ICE table was 0.2. We know O2 was 0.2. All right? And we're given a value of Kc, so we can put that here, 1.0. So now you can see what our mission is going to be. It's going to be to use this part of the equation to solve for X. Once we have X, then we can figure out what the equilibrium concentrations were. All right? So I'm going to do a little trick here, and it's going to save us a lot of trouble. We have 2X squared over, oh my gosh, these are supposed to be, I completely botched the denominator, pardon me. It's 0.2 plus X, minus X. And 0.2 minus X. That's our denominator. Goodness, that was a big mistake. All right, so fixed it. What I do want to point out, though, is that those guys are what we call a perfect square. All right? So what I mean by that is if you were to FOIL them, you could rewrite the expression like so. All right? That really saves us some trouble, trust me. We'll see an example where we're not so lucky. All right? Next. This is cool because I have squared here and squared here. So what I can do is I can take square root of both sides, and that will greatly simplify this equation. So I'm going to move to another slide, and I've got 2x squared over 0.2 minus x squared. And if I take the square root of that whole thing, I also need to take the square root of the other side, which was 0.10. All right? So when I take the square root of the left side, that reduces this guy down. And the square root of 0.1, let's see. Is equal to plus or minus 0.316. All right? We have to be careful there because square roots, they can give us a positive root or a negative root. So since I have both roots, I need to solve x by setting it equal to both roots. All right? So what I'm going to do first is the positive root. So I've got 2x over, let's see, 0.2x equal to positive 3.16. I'm sorry, 0.316. All right. So solving for x, I'm going to multiply both sides by the denominator. I'm going to distribute the 0.316 through. So I'm going to take 0.316 times 0.2, and that gives me 0.063 minus 0.316x equals 2x. All right, and then I'm going to add 0.316 to both sides. All right, and I can combine those terms since they both end in an x, and then I can divide both sides by 2.316, and that gives me a number of 0.027. All right, now I'm going to do the same thing for the negative root. Oops. It was negative 0.316. All right. And we're going to quickly see that this doesn't work out. All right. And the reason why is because when I multiply both sides by the denominator, I'm going to get negative 0.063 plus 0.316x equals 2x. So negative 0.063 will be equal to 1.684x. And x in this case would be a negative number, which would give me a negative concentration, so that makes no sense, so we cannot use the negative root. And you'll find you only can use one root in each case. So make sure you check both roots. It's not always the positive root that wins, but in this case it did. All right, so that said, I finally found my value of x at 0.027. All right, now, this is where you kind of get a little bit lost, and that's why you have to have this systematic approach. What in the heck was x again, right? So if you keep good bookkeeping, you go back and you say, oh yeah, x was what? These equilibrium concentrations. So all you have to do now is plug in x to each one of those expressions, and you're going to get the equilibrium concentration for each species. All right? So let's just be complete and do that. And we're going to go ahead and put an x through this because we don't need the negative root. And we have 0.2 minus x was equal to the concentration of the N2 and the O2. And in this case, it was 0.2 minus 0.027. So that is going to give us a concentration of 1.73 for both the O2 and the N2. All right. For the NO, that was just simply 2x. Which in this case is 2 times 0.027, which is 0.054 molar. All right. Woohoo, we made it. Okay, here's the good news. We had a systematic approach for it, all right? Hopefully you can follow that. It's going to take some practice. I'll put up some practice examples, but work through this. Make sure you get a nice flow for your bookkeeping. Make sure you can get the same numbers I did. Check out the algebra. Practice the algebra if you need to, or reach out. if you need a little bit of help with the algebra. All right? And you should be able to get these numbers. We're going to step it up to a little bit more difficult of one. All right? And let's just go ahead and do it. All right? So we're going to change our reaction now to N2O4 gas. And we're going to make 2 moles of NO2 gas. So at first glance, like, well, that looks easy, right? Well, we'll see. Kc is equal to 0.36 at 100 degrees C. I don't really care about the temperature anymore, all right? What they're telling us now is that a reaction mixture at this temperature initially contains NO2 at 0.1 molar. All right? Find the equilibrium concentrations of NO2 and N2O4 at this concentration. All right? Okay, so this is initial. So what the heck are the equilibrium concentrations of these guys? All right? So we're going to go through the same steps we did on that last one. All right? First step was set up your Q expression to figure out where you are. All right? So it's molar. So QC in this case is equal to the NO2 squared over N2O4. All right? And our N2 was 0.100 squared over 0. You can't divide by 0, right? Well, you can because you essentially approach infinity, all right? So what is the value of QC? It's infinite, right? So it's gigantic. It's way bigger than KC, so we have way too much product, so we're going to move to the left. Or towards reactants. Okay, no big deal. It just throws in a tiny twist into our problem. All right, so let's set up the ice table. All right, so N2O4 going to NO2 ice. All right, initially we had none of this guy, and we had 0.1 molar of that guy. All right, so how are they going to change? This is where you got to be careful. You just don't want to start slapping negative signs on this side and positive signs on this side. All right, that's where that Q came in handy. Right? Q told us we were doing what? We were going to consume this guy and make this guy. All right, that's what Q told us. All right, and now we just need to figure out that factor. This guy is going to be a plus x, and this guy is a minus 2x. All right, so at equilibrium, this guy is just simply x. Nice. And this guy is 0.1 minus 2x. All right? So there we go. Ice table is complete. Now what we need to do is take these equilibrium values and set them equal to k and solve for x. So k, C, is equal to the concentration of NO2 squared over the N2O4, right? And that was going to be 0.1 minus 2x squared over just simply x. And our value of Kc is 0.36. So this is the important part here. All right, we're going to extract that down here, and we're going to say 0.36 is equal to 0.100 minus 2x squared over x. So we immediately run into a problem here. Last time, we were able to just take a square root, all right, and kind of smooth sailing from there. Why can't we take a square root in this case? Well, you certainly can. Nothing wrong with it. Problem is, you're going to get rid of this exponent, but then you're going to be left with an exponent of 1/2 there. And you're going to have what we call polynomials. And when we have polynomial functions, in order to solve those, one of the surefire ways to do it, especially when we're dealing with x squared and x, is our old buddy, the quadratic formula. All right? Now, the quadratic formula is not a lot of fun to do on a calculator, but it's amazingly easy to do on the internet. And we are in a distance learning environment where you can access the internet. And one that I'll give you, since you're at home, when you're dealing with a quiz or a test, is Google Quadratic Formula Solver or something like that, and it'll allow you to plug in all your neat roots. All right, so what we're going to do is go ahead and solve this, derive the quadratic equation, and I'm going to open up my computer, hit the Quadratic Formula Solver, and we're going to be good to go. All right, so that's a little treat for you for being a distance learner. All right, okay, let's get to work. Where were we? Oh, we got it right here. So what I'm going to do is go ahead and get this thing in the quadratic formula format, all right? And that format is the following. We have ax squared plus bx plus c equals 0. All right, so when we get our polynomial in that form, what we can do is we can solve for x using the quadratic formula. It's equal to minus b plus or minus the square root of b squared minus 4ac over 2a. All right. So again, those of you that want to challenge yourself and solve it that way, that's fine. But we can certainly go to a quadratic formula solver, type in our value for b, type in our value for a, and type in our value for c, and we get our x within milliseconds. Very nice. So the challenge actually for this is going to be to get our equation into that form now. All right, so what we're going to do is we're going to deal with this guy on the next slide and get him into this form. All right, so let's get to work. So 0.36 equals 0.100 minus 2x squared over x. Just make sure I get all that right. Okay. So first thing I'm going to do is just multiply both sides by x. So I get 0.36x equals 0 minus 2x squared. All right. So then I have to do something here. I have to FOIL this guy out. All right. So when you FOIL it, some of you may be sitting there, when are we ever going to use this in Algebra 2 back in high school? Well, here's the day. All right, so all right. So after foiling, I should have that. And then what I'm going to do now is get the 0.3x over to the, I'm going to subtract 0.3x from both sides so I get my 0. And now I'm going to collect the two x terms together. Make sure I got that right. It's 0.4 and 0.36 would be 0.76 x plus 4x squared equals 0. So to get it in that ax squared plus bx plus c format, I'm going to do a little bit of rearranging. 4x squared minus 0.76x plus 0.01 equals 0. So now my a is equal to 4, b is negative 0.76, and c is 0.01. All right, so I'm going to head over to the quadratic calculator real quick, and I'll report my value of x, or two of them, because I get two roots. All right, I'm back, and the one I found was mathisfun.com. Damn right it is. Quadratic equation solver. All right, so Google gave me that, and it's pretty cool. You put in the A, B, and C, and it shows you a plot. And I got two positive roots in this case. And the x's I'm getting for my two roots are 1.7, I'll round it up to 1.76, and 0.014. Okay? So those are my molar concentrations. Now what I'm going to do is only one of them is going to work. All right, so let's see if we can eliminate one very quickly. Yeah, we can. All right, if we look here, our equilibrium concentration of the NO2 is 0.1 minus 2x. So if I plug in 0.176, it's going to blow up and give me a negative concentration. All right, can't do that. So this guy can't work. All right, it's too big. So what I'm going to do is this one. All right, so my equilibrium concentrations of the NO2, that was equal to 0.1 minus 2x. In that case, it's 0.1 minus 0.028. And I get 0.072 molar. Right. Very nice. And then for the concentration of the N2O4, that's just simply X. Do that all day, right? It's 0.014. Woo! Big one. We nailed it. All right. So go back to the Wayback Machine, Algebra 2, FOIL, quadratic, all that fun stuff. And these problems with the systematic approach won't be too terribly difficult. Now, again, a quiz or an exam, you can use that Math is Fun quadratic equation solver if you would like to. It's much more accurate and effective. All right, so that does it for this video. All right, when we come back, we're going to finish up our discussion of chemical equilibrium with Le Chatelier's principle that is the major part of Lab 6. So I know I posted Lab 6 today, but you can hold off another day on it until we get through our lecture of Le Chatelier's principle if you don't read ahead. All right. Thank you very much.